Today on AI Paper Podcast, we're diving into Code2World, a GUI World model via renderable code generation. This is from Yuhao Zheng, Lian Zong, and colleagues at USTC, Alibaba, and Oxford.
Right.
And the core idea here, the big breakthrough, is a new way to build world models for GUI agents. So instead of trying to predict the next screen with diffusion, which is all pixels, or with, text descriptions, this model predicts the actual HTML code that generates the screen.
It's a fundamental shift in the representation.
It's so clever. The model takes the current screenshot, takes an action, and then it just generates the HTML for the next screen. You feed that to a browser, and boom, you get the exact visual state.
No guesswork.
And the results are wild. Their 8 billion parameter model beats giants like GPT-5 and Gemini 3 Pro Image on this task. And get this. When they use it as a simulator for planning, it boosts the Gemini 2.5 Flash agent's success rate by 9.5%.
Which is a huge leap.
It's a total shift from, let's say, hallucinating pixels to actually compiling futures.
Yeah, it's the difference between an artist sketching a user interface and an engineer actually building it. One is just a picture, the other has real structure.
Okay, let's get into that. We talk about agents all the time, these systems that can control our phones or browsers, but they're still pretty brittle. Why are they struggling so much with reliability?
It really comes down to a lack of foresight. If you or I see a delete button, we instinctively run a little mental simulation.
Right. I know it's going to pop up a confirmation box.
Exactly. You anticipate the state change. You have a mental model for the physics of the software.
Okay.
Most agents today they don't have that.
Yeah.
They operate without a world model. They see a state, they perform an action, and they just kind of hope the next state is what they wanted.
So they're just flying blind.
Pretty much. And without that simulation step, that ability to pause and think, wait, if I click this toggle, I might lose my internet connection, they make really bad mistakes.
So we need a model that can simulate that equation. Current state plus action equals the next state.
That's the goal.
Now, people have tried this before, right? With text-based models, pixel-based models. Why haven't those worked?
Well, text is just too abstract. If a model predicts the menu opens, that's fine, but it's spatially useless. It doesn't tell the agent where the menu is or if it's covering up another button.
It lacks any kind of precision. So what about pixels? Diffusion models are incredible now.
They are, but they have what the authors call the pixel problem with GUIs. Diffusion models are great at texture, at making things look artistically coherent. They are not great at logical rigidity.
What does that mean in practice?
It means you get these weird artifacts. You get melting buttons, text that looks like, alien gibberish, and straight lines start to get all wavy.
It looks more like a dream about an app than the actual app.
Exactly. And for an agent that needs to click on a very specific coordinate, a dream version is completely useless. There's no structural controllability.
Which brings us to Code2World. The whole insight is that GUIs are made from code HTML DOM trees, so we should be predicting that, not the pixels.
It's one of those things that sounds so obvious in hindsight. If you predict the HTML, you completely sidestep the hallucination problem.
How so?
You just feed that HTML into a deterministic renderer, a browser engine, and it draws the screen perfectly. Lines are straight, text is sharp, the layout is always valid.
So you're swapping a probabilistic, kind of artsy drawing process
for a deterministic engineering-based rendering process, yes.
Yeah.
You still use a model to guess the code, but once the code is written, the output is guaranteed to be structurally sound.
Let's talk about the data, though, because that feels like the biggest roadblock. You'd need a huge data set that pairs screenshot A plus an action with the perfect HTML for screenshot B. And that just doesn't exist, right?
No, it absolutely does not. Most data sets just give you pixels and maybe some coordinates. They don't have the clean underlying code. So the authors had to build their own. They call it AndroidCode.
And they didn't do this by hand. They used a synthesis pipeline.
Right. And this is really where it gets clever. They used GPT-5 to reverse engineer screenshots into HTML.
But hold on a second. GPT-5 hallucinates too. If you ask it to write the code for a complex screen, it's going to make mistakes, isn't it? It'll miss a button or get a color wrong.
It does, for sure. And this is where the paper gets really interesting. They built what they call a visual feedback revision loop.
Oh, okay. Walk me through that.
So, step 1, GPT-5 generates the HTML. Step 2, they immediately render that code into an image. Step 3, they use a visual encoder, SIGLEP, to compare their rendered image to the original screenshot.
It's like an automated spot the difference game.
Exactly. And they check the similarity score. If it's below 0.9, meaning the code didn't do a good job, they don't just throw it away.
What do they do?
They take the original image, the bad rendered image, and the broken code, and they feed it all back into GPT-5.
Tell it to fix its own mistake. Here's what you made, here's what I wanted, now fix the code.
Yes. This self-correction loop is how they generated over 80,000 high-quality training pairs without any humans in the loop. It's brilliant.
There was one other detail I wanted to pull out from the data part. These semantic placeholders.
Oh, yeah, that's crucial.
Why do they need those?
Okay, think about a shopping app. You have the layout, the buttons, the price, but then you have the actual product image. Maybe it's a specific photo of a red running shoe.
Right.
Asking a model to generate the pixel-perfect binary data for that specific shoe is, well, it's super inefficient and not the point.
It's an asset problem, not a layout problem.
Exactly. So the model learns to use placeholders. Instead of generating the image, it just writes a tag, like IMG, red shoe. The renderer knows to just put a box there.
So it forces the model to focus purely on the structural logic of the interface, not the content or the artwork.
Correct. It keeps everything focused on interaction dynamics.
Okay, so they have this great data set. Now for the training, they're using a Qwen 3 VL8B model. How do they teach it to be a world model?
It's a two-stage process. Stage one is what they call the cold start. It's a standard supervised fine-tuning, or SFT. They feed it the dataset. Input is a screenshot and an action. Output is the HTML.
So that teaches it the syntax, how to write valid HTML.
Exactly. It learns the grammar of the web. But SFT has a big limitation. It just treats the code as text. The model is predicting the next word. It has no real understanding of the visual consequence of that code.
It's like learning to write sheet music without ever hearing the song.
That is the perfect analogy. You might get the notes right, but you have no idea if it sounds awful. So they move to stage 2, render-aware reinforcement learning, RARL.
This is the hearing the song part.
This is where they actually render the code during training and grade the model on the visual output.
But that seems tricky. We just talked about the placeholders. If the model renders a box but the real screen has a photo, how do you grade that? Standard pixel comparison would fail.
It would. So you can't use standard metrics like SM. Instead, they use a VLM as a judge. They have Echelon Language Model act as the reward function. And it's a dual reward system.
Okay, break those down.
First is RSEM, the visual semantic reward. The judge VLM looks at the predicted screen and the real one, and it checks the layout. Is the button in the right spot? Is the text aligned? But it's specifically told to ignore style differences from placeholders.
So it's judging structure, not style.
Got it. Second is RACT, the action consistency reward. This is the crucial one for an agent. The judge checks the logic. If the action was click the search button, did a search bar actually appear?
It's verifying the cause and effect.
Precisely. This is what forces the model to actually learn the dynamics of an interface, not just what screens look like.
Let's get to the performance. They put their 8B model up against a 72BQ model and Gemini 3 Pro image. Usually bigger is better. An 8B model shouldn't be beating a 72B model.
But it does. I mean, it demolishes it. In terms of functional logic, that action adherence metric, the Code2World model scored a 92.7, while the massive 72B model got a 55.
Whoa. That is a massive gap. Why? Why is the specialist so much better?
It's all about the representation. The large models are pixel generalists. Code2World is a code specialist. The paper talks about this idea of structural rigidity.
Define that for us.
Okay, if you use a pixel model like Gemini, and you take an action that totally changes the screen-like clicking from a list to a detail page, the pixel model struggles. It kind of ghosts the old image onto the new one. It can't let go of the previous frame's pixels.
It's like it's blending the past and the future.
Yeah, exactly. But Code2World just generates a whole new block of code, a fresh DOM tree. It doesn't care what the last screen looked like, so it handles these huge layout shifts perfectly.
It's writing a new web page, not trying to Photoshop the old one.
That's the perfect way to put it. And they tested this on apps the model had never even seen before, and it still held up. So it learned the general rules of how GUIs work. It didn't just memorize some screens.
So we have a simulator that's fast, accurate, and small. The big question is, does this actually help an agent perform better?
Right. This is the so what of the whole paper. And they integrated it into a pipeline they call propose, simulate, select.
How does that work?
Okay, take the Gemini 2.5 Flash agent. Let's say you ask it to turn off the Wi-Fi. Normally, it just sees the toggle and clicks it.
C button, click button. Standard stuff.
With Code2World, it's different. First, the agent proposes a few possible actions. Option A is click the toggle. Option B is click back. Code2World then simulates the future for each of those. It generates the HTML and renders what would happen.
So the agent gets to peek into the future before it commits?
Yes. The score module looks at those simulated futures. It sees that clicking the toggle leads to a screen that says connection lost and realizes that's a bad outcome. So it gives it a low score and the agent picks a better action.
It filters out its own mistakes before it can make them.
And the impact is huge. On the Android World benchmark, the baseline Gemini agent had a success rate of about 41%. With the Code2World simulator added, that jumped to almost 51%.
That's nearly a 10% absolute improvement. We're usually fighting for fractions of a percent in these benchmarks.
But a 10% jump just from adding a simulation layer it's a massive validation. It proves that this kind of deliberative planning is the next big step for these agents.
I do want to touch on the limitations, though. This works great for anything with a DOM or a view hierarchy, but what about everything else?
That's the boundary. It works for your settings menus, your web browsers, your shopping apps. It absolutely does not work for games or, highly custom graphical interfaces. You can't use this to play Call of Duty Mobile.
So it's for the boring but essential digital tasks.
Which, let's be honest, is 95% of what we actually want these agents to do for us.
There's a bigger implication here for training data, isn't there? We always talk about the data wall, about running out of human text and images.
I think it could potentially solve that for the GUI world. If your simulator is good enough to generate infinite, valid, and diverse user journeys, you can use that synthetic data to train the next generation of agents.
So you don't need to record a human booking a flight 10,000 times.
Nope. You just have the model simulate it 10,000 times with slight variations each time. You create this self-reinforcing loop where the simulator makes data to train a better agent, which helps you build a better simulator. It's a synthetic data engine.
It really feels like a turning point. For so long, the approach to digital worlds was through a computer vision lens. Just look at the pixels. This paper is arguing that looking isn't enough. You have to read the source code.
We are absolutely moving from agents that just see the interface to agents that understand it. When you understand the HTML, the DOM, you understand the rules of the environment. And that makes you a much more capable and, frankly, much safer player.
A really compelling argument for code-native world models. For anyone listening who wants to see the visual proof, I'd really recommend looking at Figure 3 in the paper. The comparison between the melting button diffusion outputs and the clean Code2World renders, it's night and day.
The pictures really sell the whole story.
That wraps up our look at Code2World. Thanks for listening to AI Paper Podcasts. We'll see you next time.